are the Lagrange interpolation method. And then number 2, they are the Newton divided difference method. So before we discuss each of them, we know that a polynomial function is a function of this nature, a0 plus a1x plus a2x squared plus a3x power 3 . So this is a polynomial function of degree n. So if n is 1, or say if n is 0, then f of x equals to a0. So this is called a constant function. So if n is 1, then f of x will be a0 plus a1x. This is called a linear function of polynomial. When n is 2, I will have f of x equals to a0 plus a1x plus a2x squared. And then remember, in this case, a1 must always be non-zero. In this case, a2 must always be non-zero. So what name do we give to this kind of function? Correct, quadratic. So these are quadratic polynomial or quadratic function. So quadratic function or polynomial. When n is 3, we'll have f of x equals to a0 plus a1x plus a2x squared plus a3x power 3. Then the condition is that a3 must be non-zero. And what name do we give to this? Cubic function, correct. This cubic function of polynomial. When n equals to 4, we'll have f of x equals to a0 plus a1x plus a2x squared plus a3x power 3 plus a4x power 4. So a4 should be non-zero. And what name do we give to a polynomial of degree 4? Quartic, correct. So this quartic function or polynomial, etc. So given 2 points, say x naught, f of x naught, and x1, f of x1, we can define, if we go back to your form 2, if I have 2 points, I can define a line, okay? If I have 2 points, I can define a line. So the line is just a polynomial of degree 1 or a linear function. So 2 points defines a linear function or linear polynomial of degree 1. Linear function or linear polynomial or polynomial of degree 1 all mean the same. Now, if we have 3 points, say x0, f0, and I hope you remember that f0 means the value of the function at x0, x1, f1, x2, f2, we can define a quadratic function. If you remember your linear algebra work, there are cases whereby you have been told that there's a function which defines a function that passes through, say, 3 points, say 2, 3, maybe given, say, 5, 10, and say 12, say 93. And then they ask you, find a polynomial that passes through all these 3 points. So if you remember well, then this is a kind of the function that you are using. And so by each value of x, you replace into the general structure of the quadratic function, and then you form a system of 3 linear equations, then solve for the unknowns, a0, a1, and a2. Then you get that given function. So if we have 3 points, they can help us to define a quadratic function or a polynomial of degree 2. Now, if these are 3 points, not 2, so these are 3 points. So x not f, okay, so this was the first one. So then now, given 4 points, given 4 points, say x0, f0, x1, f1, x2, f2, and x3, f3. They can define a polynomial of maximum degree of, or the maximum degree that these points can define. Three, correct. So we can define a polynomial of degree 3. So which is simply cubic function. Then if we continue in a similar manner, and you are given n points, say x naught, f naught, x1, f1, all the way up to xn, fn. What is the maximum degree polynomial that these points can define? We follow the same order. N minus 1, correct. So we can define an n minus 1 degree polynomial, or simply a polynomial of degree n minus 1. So which simply means that if you have been given some arbitrary number of points, then to determine the maximum degree that those points can form a polynomial, then it's simply the number of points given, you subtract 1. So that was just a by the way. So let's see how to derive the Lagrange interpolation formula, and thereafter we'll see how we can apply it. So the Lagrange interpolation. And it should be noted that the methods we discussed under unequally spaced mesh points can as well be applied for equally spaced mesh points, but the reverse is not true. So to derive the Lagrange interpolation formula, we let y equals to f of x be a function which assumes or which takes the values f of x naught, f of x1, f of x2, all the way up to f of xn, corresponding to the values x equals to x naught, x equals to x1, x equals to x2, all the way up to x equals to xn, respectively, where x naught, x1, x2, all the way up to xn are not necessarily equally spaced. So that statement means that they may be equally spaced or they may be unequally spaced. So it applies for all cases. So if I have values x naught, x1, x2 up to xn as my tabular points, how many tabular points do I have altogether? From x naught to xn, how many values are those? N plus 1, correct. So since n plus 1 values of the function are given, corresponding to n plus 1 values of x, we can represent y equals to f of x as a polynomial in x of degree. So what will be the maximum degree that this n plus 1 points can define? N, correct. So Paul say that we really we just count the total number of points, we subtract 1. So n plus 1 minus 1 is n. So with n plus 1 values of the function corresponding to n plus 1 values of x, then a polynomial of at most degree n will be used to approximate all those values. And then we say let y equals to f of x now be given by a naught into x minus x1 times x minus x2 times x minus x3 times x minus xn, then plus a1 into x minus x naught, x minus x2, x minus x3, all the way up to x minus xn, plus a2, x minus x naught, x minus x1, x minus x3, all the way up to x minus xn, plus other several terms, plus an into x minus x naught, x minus x1, x minus x3. Anyone who is able to follow what I'm doing, what will be the subscript of this last x value? N minus 1, correct. N minus 1. I hope you have discovered what is happening on how we are representing our n degree polynomial for this case. That when the coefficient is ai, then in that product, we don't have x minus ai, x minus xi, okay? That's what is happening, that in the first term, you see we have the coefficient a naught, but in this product, there's no bracket with x minus x naught. And when we have a1, there's no bracket x minus x1. When we have a2, there's no bracket x minus x2. And when we have an, there's no bracket x minus xn. And you should appreciate the fact that if you are to open the brackets for each term, you'll find that the highest power of x is n, because in each term, there are n such kind of brackets, x minus xi. So I can make that clearer here. So let's call this one equation 1. Each term in equation 1 is a product of n factors in x of degree n. So then now the goal is to find the values of these unknown constants. So goal to determine the values of unknown constants AIs. In each of the terms that defines the f of x function. And for us to be able to get these unknown constants AIs, we'll start by fixing so let's x be x naught. Because we have been told that this function y equals to f of x is defining the values of the function at x naught, x1, x2, x3 up to xn. So with this structure of the function, so it means that when I put x naught, then still must satisfy that equation. So putting x equals to x naught, then question 1 becomes f of x naught. So where there's x in all this equation, I'm replacing x naught. So you should be able to see that the only term that will remain will be the first term. Other terms will go to 0. Are you able to appreciate that? That whenever we replace x for x naught in this equation 1, then the only term that remains is the term with the coefficient a naught. All other terms will be 0. Are you able to see that? Yeah, because each of the remaining terms from this one with a1, a2, a3 up to an, there's a bracket that has x minus x naught. And so because we're replacing where there's x by x naught, so like here we'll have x naught here. So x naught minus x naught will give us 0. So 0 times everything here will render that term to be 0. Similarly, in A2, we'll have x minus x naught minus x naught. This will be 0, so makes everything 0. And all other terms that follows will have a bracket x minus x naught. So on replacing x for x naught, we get 0. So all those other terms will be 0. So the only term that remains will be a naught into so we'll have a naught into x naught minus x1, x naught minus x2, x naught minus x3, all the way up to x naught minus xn. So which means, remember, f of x naught is already given. So we have defined the value x naught. So the value of the function at x naught is already defined. So you can make a naught the subject, and this will be f of x naught divided by x naught minus x1, x naught minus x2, x naught minus x3, all the way up to x naught minus xn. You can call this one 2. So this is a value of the unknown constant A naught. So similarly, let x to be x1. Then equation 1 becomes f of x1. So can you tell me the terms which, or the term which will remain, or the terms which will remain in 1 after replacing x for x1? The term with a1 is the only one that will remain because other terms have x minus x1, okay? Yeah, so because when you put x1 in this first term, this will give us a 0. So 0 times everything there will be 0. Similarly, in A2, there's an x minus x1. A3 will also have an x minus x1 up to an. We'll have an x minus x1. So the only term that remains will be this term with coefficient a1. So we'll have a1 into x1 minus x0, x1 minus x2, x1 minus x3, x1 minus xn. And when you make a1 the subject, you get a1 equals to f of x1 divided by x1 minus x0, x1 minus x2, x1 minus x3, all the way up to x1 minus xn. So call this one 3. So this is the value of the unknown constant, a1. Are you able to predict when you replace x for x2 in equation 1? What relationship do you get? We'll have f of x2 equals to which term remains? Term with a2, correct. So a2 into x2 minus x0 multiplied by x2 minus x1 multiplied by x2 minus x3 up to x2 minus xn, correct. So then this means that a2 alone will be f of x2 divided by x2 minus x0, x2 minus x1, x2 minus x3, all the way up to x2 minus xn. So we call this one 4. At this point in time, we should be able to predict how f3 will look like. So we can say similarly, a3 will be f of x3 divided by x3 minus x0, x3 minus x1, minus x2. Next, before we go to the last term, Or after x2 minus x3, what is the next term? Correct, x3 minus x4. And then we go up to x3 minus xn. Good. So we do the same exercise up to an will be given by f of xn over xn minus x naught, and then x1, then xn minus x2, all the way up to xn minus correct, xn minus 1. Good. So then now, maybe let's call this one question 5. All these other terms, let's call them 6. Then this one, let's call it 7. So then we say replacing two, 3, 4, 5, 6, and 7 into equation 1, we obtain okay, let me demonstrate how the structure of the f of x is going to look like just from what we have here. From equation 2, you discover that a naught is having f of x naught in the numerator, and then in the denominator, the first bracket is x naught minus x1, followed by x naught minus x2, followed by x naught minus x3, all the way up to x naught minus xn. So when we go to the f of x first term, it's the same thing. Like the only difference is that now where there's x, we are replacing by x naught. So there's an x naught minus x1, there's an x naught minus x2, there's an x naught minus x3, all the way up to x naught minus xn. Then if you go to the a1 value, the denominator has x1 minus x naught. Then next term is x1 minus x2. Next term is x1 minus x3, all the way up to x1 minus xn. When we go to the f of x where there's a1 coefficient, still the same thing. So we'll have x1 minus x naught, x1 minus x2, x1 minus x3, all the way up to x1 minus xn. So there's some symmetry on how the denominators in each AIs look like, and the factors involving x in the original f of x function. So therefore, to write the first term after replacing the value of a naught is as good as having this fraction whereby these brackets involving x values are actually having some similarities in the second value for each bracket, both in numerator and denominator. And the only difference is that when you are defining a naught, then the starting value in the denominator is x naught. When you are defining a1, the starting value in the denominator is x1. Similarly, when you are defining a2, the starting value of x in the denominator, each bracket will be x2, up to when you'll be defining an. The first term in each of the brackets in the denominator will be xn. So therefore, when we do this replacement, we get f of x will be given by, first term will be x minus x1, followed by x minus x2, followed by x minus x3 all the way up to x minus xn, then you multiply by f of x naught divided by x naught minus x1, x naught minus x2, x naught minus x3, all the way up to x naught minus xn. So that is how the first term will look like after replacing the actual value of a naught. Then plus the second term that involved a1 will be x minus x naught, x minus x2, x minus x3, all the way up to x minus xn, divided by x1 minus x naught, x1 minus x2, x1 minus x3, all the way up to x1 minus xn, then you multiply by f of x1. So there's always some symmetry on how the coefficients of f of xi's are. Then next term will be x minus x naught, x minus x1, x minus x3, all the way up to x minus xn times f of x2, then x2 minus x naught, x2 minus x1, x2 minus x3, all the way up to x2 minus xn, plus other several terms. The nth term will be x minus x naught, x minus x1, x minus x3, up to x minus, what is the value of x here? Subscript of x in this last term. What is the last subscript for x value? This is 2. What will be the last subscript for x in this last term? X. Correct. Xn minus 1. So this is now how the f of x function will look like. So this is what we call the Lagrange interpolation formula. So if we call it h, so this is equation 8. So equation 8 is what we call the Lagrange interpolation formula. So note that sometimes in other textbooks, instead of us writing f of x naught, we will write f naught, or we'll write y naught. Instead of writing f of x1, we can write f1 or y1. So they will still be meaning the same thing. Or instead of writing f of x2, we can use f2 or y2, etc. So h is used to find or approximate y, which is equals to f of x when given some xi values. Xi and f of xi values. So when we interchange the roles of x and f, we obtain the inverse Lagrange interpolation formula used for finding or approximating x when given values of xi, fi. This is what I mean. To rewrite the inverse Lagrange interpolation formula, where there is x, you replace by y, or f, and where there is xi, you replace by yi or fi. So then from 8, we have x value is given by f minus f naught, f minus f1, f minus f2, f minus f3, all the way up to f minus fn, divided by f naught minus f1, f naught minus f2, f naught minus f3, all the way up to f naught minus fn, multiplied by x naught plus f minus f naught, come in, f minus f minus f2, f minus f3, all the way up to f minus fn, multiplied by x1, f1 minus f naught, f1 minus f2, f1 minus f3, all the way up to f1 minus fn. Come in. Up to f minus f naught, f minus f1, f minus f2, f minus fn minus 1, you multiply by xn, fn minus f naught, fn minus f1, fn minus f2, all the way up to fn minus fn minus 1. So where I'm putting f, you can as well put y. So sometimes we use y or f just to mean the value of the function itself. So this is the inverse Lagrange interpolation formula that can help you to find a known value of x when you have a value of y or value of f. While the first method, equation 8, is the direct or simply the Lagrange interpolation formula, which will help you to approximate the value of a function at a given value of x. So an example, use the Lagrange interpolation formula to find a polynomial that fits all the points given in the table below. So this is the table, x value, functional value. So x is -1, 0, 1, and 2. When x is -1, y is 0. When x is 0, y is -1. When x is 1, y is 0. When x is 2, y is 15. So how many points are we given? 4 points. So by default, we label this one as x0, x1, x2, x3. Then x0, then obviously this must be f0, this must be f1, this must be f2, this must be f3. So they have not specified the degree of the polynomial we need to use to fit the values in the table. The question is just saying that to find a polynomial that fits all the points given in the table. So which means then now we have to take it in the general form. If we have 4 points, then the degree, maximum degree that we can define for those 4 points is if I have 4 points, then my polynomial can go up to degree 3, correct. So since we have 4 points, then we can define a polynomial of degree 3, i.e., we expect our polynomial to be of this form, f of x equals to, so sometimes we can write P3 to mean a polynomial of degree 3. It will be a polynomial of this form. So the problem wants us to use Lagrange interpolation. So how many brackets? So remember this Lagrange interpolation formula, equation 8, can be written as y equals to f of x equals to L naught of x, f naught, plus L1 of x, f1, plus L2 of x, f2, plus all the way up to ln of x times fn. That's in short, that's how we can write the short form of question 8, where LIs are those coefficients of fi values. So how many brackets of x will be defining each of our L value if we have to deal with a polynomial of degree 3? You need to multiply how many brackets of x to get power 3? You remember this formula here, the brackets in each coefficient of fi, we have n such kind of brackets, so that when you multiply, we get a degree n. So the question is, if ours is degree 3, how many such kind of brackets do I need? 3. I only need 3, so that x minus xi, x minus xi plus 1, x minus xi plus 2. When I open the bracket, then I'll only need 3 x's to give me up to x power 3. So there's, in our case, the formula will be y, which is the function f of x, will be L naught of x times f naught plus L1 of x times f1 plus L2 of x times f2 then plus L3 of x times f3. So then now, what is the value of f naught from our table?
0.
0. So I'll have 0 times L naught of x. F1, negative 1 times L1 of x plus F2, 0, L2 of x2, F3, 15, L3 of x. So then now this will give us negative L1 of x plus 15 L2 of x, L3 of x. So where so the first thing you need to know how many brackets you need. And then so in each case, you need 3 linear brackets that when you multiply, you get x power 3. So just listen before you write. When we say L1 of x, then it means that we are dealing with x1 value. So then in each denominator, you start with x1 value, x1 value, x1 value. And then when you say L1 of x, then the starting value in each of the bracket in the numerator will be an x. This will be an x. This will be an x. Is that okay?
Yes.
Good. So remember, we are only dealing with 4 numbers. There's an x0, there's an x1, there's an x2, and there's an x3. So when your starting value in the denominator is an x1, then you cannot put x1 minus x1. So which means that to define L1 of x, you are not going to subtract x1 in any of the bracket, because if you do that one, you'll be introducing a 0 in the denominator. Because remember, the brackets are usually symmetrical in the second difference of each bracket. So if I have an x1 here, then it means that for me to define L1 of x, I'm not going to subtract any x1 in any bracket. So it means that my starting value will be x0, followed by
X minus x2.
x2, and then x3, okay? Yeah. And because these things are symmetrical, when this is x0, then this must be x0. When this is x2, this must be x2. And this is x3, this must be x3. Okay. So we'll do the substitution. Let's just define L3 first before even we do substitute, because we know what x1 is, we know what x2, x3, and x0 is. So for L3, in the numerator, you start with x minus, x minus, x minus. And then denominator will start with x3, because there's a 3 here. So you'll have x3 minus, x3 minus, x3 minus. So when I'm having x3, then it means that I'll not be subtracting any x3 in any of those brackets. So my starting value will be x0 followed by x1, then x2, correct. And when you put an x0 here, then this must also be x0, this must be x1, this must be x2. So then now, let's substitute in the values. Well, I have x minus.
Right.
Okay. So once you have defined Li in the general form, then you put in now the actual values from the table given. So my first numerator will be x minus.
Minus 1.
So x minus minus 1 will be x plus 1. Then next, x minus.
Minus 2.
X minus 2.
1.
X minus 1, then x minus. X minus x minus 2. Then in the denominator, I'll have my x1 value is 1. I subtract minus minus 1, so 1 plus 1. So this is 0, not this is 0, not x1. So this is 0 minus 1, then 0 minus 2. I hope you can see where I'm getting the 0. Yeah, because from this table, x1 is 0 here. So this will give us x plus 1, x minus 1, x minus 2, 1 times minus 1 times minus 2. So I'll have x squared minus 1 into x minus 2 divided by 2. Able to see where I'm getting that positive 2 and the first bracket, the numerator? Good. So when I open the brackets in the numerator, I'll have x power 3
X power 3 minus 2x
minus 2x squared. And then minus x plus 2, correct. Then let's define L3 of x. So L3 of x, I'll have x minus minus 1 is plus 1 into x minus 0 into x minus 1, correct. Then I'll have 2 plus 1, 2 minus 0, and then 2 minus 1. So I'll get now x plus 1 times x minus 1, then 3 times 2 times 1. So I'll have an x into x squared minus 1 over 6. So which when you multiply, you get x power 3 minus x over 6. So therefore now, f of x, which was minus L1 of x plus 15, or this 15 L3 of x? Yeah, that's what the polynomial reduced to after replacing the fi values in the formula. So can you substitute, negate the L1, which is obtained from here, and then multiply this by 15, collect like terms and tell me what will be the value of f of x. Replace the values of L1 and L3 into f of x, and then simplify, collect like terms. Then tell me how does your f of x look? Shamaliza zile. Sijaandika hizi bado. Hizo ni nimeandika. But you oh yes, basi pepo hizi. Sawa. Kama ungeandika ingekuwa rahisi. What if your f of x after simplification What is the coefficient of x power 3? Should be 2. So 2x power 3. And what is the coefficient of x power 2? 1, correct. What is the coefficient of x?
-2.
Minus 2. And what is the constant term? Minus 1, correct. You see, this is the problem we are solving last week, and it's exactly the same function that you obtained. So we have actually solved one problem using 3 different methods. And at the end of the day, we should get the same answer. So that is what we obtained. To make more clarification on this application of Lagrange interpolation, note if the question was find f of, say, 1.5. If we have the same table and they ask us to find the value of f of 1.5, then you will actually do exactly the same thing. But instead of writing Li's of x, then you'll be putting where there's x by 1.5, 1.5, 1.5, 1.5. So 1.5, 1.5, 1.5, 1.5, 1.5, 1.5. So that when you are defining these Li values, you don't have to go up to the polynomial itself. You'll be replacing where there's x by 1.5. So 1.5, 1.5, 1.5. So here the L1 of 1.5 will be a number. It will not be in terms of x. This will be a number. And also when you go to L3 of 1.5, everywhere there's an x, you put 1.5, 1.5, 1.5, then this also be a number. So that by the time you reach here, L1 of 1.5, L3 of 1.5, you'll be having -1 times the number you obtained for L1 of 1.5 plus 15 L3 of 1.5, the number you obtained for L3 of 1.5. And so then f at 1.5, you'll just get a numerical value without necessarily going into the polynomial itself. So when the problem asks you of the polynomial is when you'll be working with the general x. But when the problem is with specific for getting value of the function at certain value of x, then when you're writing your formula, you replace the general x by that value you are interested in. I hope I'm clear on that. Yeah, then number 2, assuming you are given, use Lagrange interpolation to find f of 1 point, to find x given f of x is 0.3887 And this is a table where this is x value, this is y equals to f of x. So we have 21, we have 23, then we have 25. So for 21 is 0.3706, 23 is 0.4068, and then this is 0.4433. So the problem is interested in finding x when the value of f is 0.3887. So by default, when you have this first number is what you call x naught. And then this becomes f naught. This second number, you call it x1. This one, you call it f1. This number, you call it x3. This number, x2. This one will be your f2. And since we need to find x given f is 0.3887, then this tells us that this is an inverse problem. So for an inverse problem, we'll write x is given by L naught of f x naught plus L1 of f x1 all the way up to Ln of f of xn. But because we are only stopping at x2, f2, so in our case, we'll have L naught of f x naught plus L1 of f x1 plus L2 of f x2. And this is a direct problem because the value of f is given as 0.3887. So you write this as x equals to L naught of 0.3887. X naught is 21 plus L1 of 0.3887. X1 is 23. And then plus 25 times L2. So which will be x equals to 21, L naught of 0.3887 plus 23, L1 of 0.3887 plus 25, L2 of 0.3887. So to define L naught of 0.3887, how many brackets will I need, by the way? Numerator and denominator will have how many brackets? From the number of points we have, there will be only 2 because we have 1, 2, 3 points. So then polynomial can be at most 2. So we'll have 2 points, then we'll have 0.3887 minus 0.388 minus. So I'll have f naught minus f1 then F naught minus F2. So this is F2, and then this is F1. Then you can always replace those values into the formula and get the numerical value of L naught of 0.3887. Then L1 of 0.3887. I'll have 0.3887, 0.3887 over F1 minus, for those who are following, this first term will be F1 minus this first bracket, F naught, and then next will be F1 minus F2, correct? So this must be F2, this must be F naught. And then lastly, L2 of 0.3887 will be 0.3887, 0.3887. So I'll have F2 minus F naught, and then F2 minus F1, correct? So F1, F1. So you already have the value of F1, F naught, and F2 in the table. So when you replace and you get your L naught, L1, and L2, you will be able now to get the value of X using this line here. And you should work X will be roughly, when you do the correct stuff, you'll find X is roughly 21.999 and some decimals. So roughly 22. Confirm that. So this is what we call, so when the problem gives you an F value and it expects you to get corresponding X value for that F, you use inverse interpolation. When the problem gives you an X value and it expects you to find the corresponding F value, then we use the direct Lagrange interpolation formula. So do more practice on how to apply Lagrange interpolation formula to solving numerical problems. And also, this is an exercise. Read and make some Newton divided differences and Newton divided difference formula. Please note that the Newton divided differences is not directly the same as the differences we have been defining in the previous chapter. So read and see how we define the Newton divided differences and also the formula used for carrying out interpolation using Newton divided differences. I'll supply some material that can help you to do that. And please, when an exercise or an assignment is given, try to work it on your own. The final exam will be very friendly to those who are revising. And numerical methods or numerical analysis is usually a very easy course to pass and also fail. It's very easy to pass and it's also very easy to fail. What will bring the difference is if you are practicing or not. If you're practicing, things will be very smooth on your side. If you're not practicing, you'll have trouble because the 2 hours time given for the final exam, you may not be able to do all the problems because usually they are lengthy computations. The only way you can match your accuracy and speed is by doing practice. So if an exercise or an assignment is given, try as much as possible to do it on your own. If you face some challenges, feel free to ask. So I wish to stop at that point, unless you want me to go up to 2. What is the verdict of many? We stop or we continue up to 2? Yes. So let's stop and please work on that assignment. I'll share the notes and recording for those who are not able to copy because of internet connection. Thank you.